Our hands and fingers are the most expressive body parts that allow us to interact with the world. Tracking hand movement has been a major technical endeavor for a long time. For major applications such as gaming, virtual reality, metaverse, and many more. However, tracking hand movement is not a trivial task. As our hands can have very diverse postures, the changing environment also magnifies the difficulty for tracking accurately. For example, having a clear line of sight path is crucial for the popular computer vision method. Unfortunately, this requirement always falls short in the real world, such as tracking at night, while users just put hands in their back. Other popular approaches, such as radio frequency and IMU-based method, cannot achieve both high tracking accuracy and mobility. We want to achieve high accuracy and robust tracking with limited overheads and costs. We propose MagX, a fully untethered and mobile hand tracking platform. Since it uses magnetic field as the sensing modality, it can track at high precision under harsh environment, such as tracking in the dark. The user only needs to put on a lightweight tracking platform. Its embedded magnetometer sensors can capture the varying magnetic field induced by wearable passive magnets, such as a ring. The raw magnetometer data will be transferred wirelessly to a mobile device for running the tracking algorithm. Our code optimization makes MagX compatible with common devices such as Raspberry Pi or smartphones. Our algorithm can achieve 5 degrees of freedom tracking of multiple magnets. Here, MagX tracks X, Y, and Z coordinates and 2 orientations of 2 passive magnets. This allows us to achieve enriched and lightweight interaction experience in augmented and virtual realities. According to our quantitative studies on both position and orientation tracking performance, MagX achieved millimeter-level accuracy within 25 centimeters. Minimizing the energy and the computing cost is essential for mobile devices, so we inspected both sensor array and a computing node. The sensor array only incurs 0.22 watts power drain for small battery pack, which typically used for smartwatches. MagX sensor array can have 8-hour battery life. For computing tasks on Raspberry Pi, the extra power drain is 0.64 watts. By throttling the CPU usage, we can also emulate the Raspberry Pi Zero platform. The extra cost is as low as 0.16 watts. This ultra-low cost feature of MagX makes it ideal for mobile applications. MagX can accurately derive the spatial information of users' hands, but there is no way to stop here. By linking the spatial data with real-world context, we can reveal rich behavioral semantics information, for example, subconscious and distracted behaviors. MagX can also support customization to better fit in these contexts. Now, we demonstrate using MagX for detecting face-touching behavior. This subconscious hand movement may lead to disease transmission. Hence, it is crucial to try hands movement on critical facial regions such as eyes, nose, and mouths. Here, by putting on the sensing platform as a pendant, magnets as bracelet, we can track the movement of both hands in real time. The continuous trajectory of users' hands can be essential information for assessing the subconscious behavior. Now, we demonstrate how MagX can help safe driving. For Level 2 and self-driving cars, when driving assistance service is engaged, it is safety critical to make sure drivers always put their hands close to the steering wheel and be ready for taking over the control. In this demo, we can embed a sensor in the steering wheel. We can track the user's bracelet in real time, detecting if the hands are properly placed for safe driving. The form factor of the passive magnet is also highly customizable. In our experiment, we tested magnets with different form factors and diameters. For example, wristband, magnetic rings, 3D printed ring bands with different sizes of the magnetic crown, and an ultra-small magnet that only has a diameter of 4 millimeters. This tiny size of the magnet can be essential for many applications. For example, capsule endoscopy is a procedure used to record internal images of human digestive system. However, it is hard to determine if the capsule is moving smoothly inside the body. By embedding a small magnet, MagX can help identify the exact location of the capsule. This demo shows using MagX as a scanner to locate the tiny magnet. The scanning procedure is mobile and easy to use, therefore benefits at-home healthcare. We open source both hardware and software of MagX for research purpose. For more detail, please refer to our paper.